Hello, everyone. Our project is about generating images from tags.
This is Wen.
This is Stefan.
And this is Abhishek.
Here is an overview of our project. Feel free to pause here if you would like to read into more details. So image generation is a popular task for deep generative models, including synthesizing images conditioned on texts. Traditionally, the input text for such tasks are descriptions or captions, which are complete sentences that carry semantic information of the scene to be generated. However, tags consist of unordered words or short phrases that are usually describing the subject or notable features in the scene, with less structure or semantics compared to complete sentences. Those are commonly seen on art sharing platforms such as Pixiv and Dumbolo, and are usually contributed by the community. On the right-hand side here, you can see some results from our generative model. Some prior works include DALL-E, which is zero-shot text-to-image generation using transformers conditioned on complete sentences, as you can see on the right-hand side. There's also AttentionGAN, which utilizes attention to synthesize details in different subregions of an image. There is VQGAN, which utilizes transformers for higher resolution image synthesis. And there's CLIP, which does image classification using language models. And there is Deep Dumbolo, which predicts multiple tags for CG images. The dataset that we used for training was scraped from the website Pixiv. We collected approximately 50,000 CG images, and those collected up to 4,000 total unique tags, and we use them directly as tokens. The images are scaled and cropped as portrait with a pre-trained anime face detector model, and then the image is scaled down to 128 by 128 pixels. The tags that we use are generated from pre-trained Deep Dumbolo tagging model, as we mentioned in prior works, because community collected tags are usually quite noisy. Our validation data is collected from the Dumbolo 2020 dataset, and then we use 2,000 CG images from those, which also totals up to approximately 4,000 unique tags. We apply the same scaling and cropping technique. Down here is some sample tags and images from our dataset.
Hi, everyone. I'll be going over to our training method. So we basically use a modified DALL-E network for our tag to CG conversion. And the first step to our training is we first train a discrete VAE. And then the VAE basically has a discrete latent space through the Compose softmax function. We encode the image to a 16 by 16 discrete token, and then with the vocab size of around 8,000. We use a PyTorch automatic mixed precision technique to train the DVAE to increase our batch size. After training the DVAE, which is the encoder and decoder architecture, we need to connect the data space and the decoder to a transformer in order to convert the text to image. So our transformer has a convolutional attention and a full attention. The input text sequence is limited to 80 text tokens, and then we will truncate them if they're running too long. And the tags are directly used as tokens. We learned the embedding size, so 512 from scratch. And we trained the full model on a RTX 3090.
We've used project inception distance as a metric to evaluate our model. We have used a final pooling layer from an inception V3 model with 8 sets of 2K images that were generated from the model using a single tag. This plot shows the comparison of training and the validation sets. So the mean of both of them are kind of close, you can see. So this shows a sample set of images generated from the model. The left one shows the real image for the tag in between. The right one shows the image generated on the same tag on 4 different iterations. So the model seems to capture lots of details in these models, as you can see. So in conclusion, we explored image generation from unstructured tags with downscaled DALL-E network and we trained it on custom dataset, which was able to synthesize recognizable thumbnail size images. And the images also show robustness on unseen validation dataset, as discussed in the previous slide. In future works, we'd like to experiment other generation models, such as conventional conditional VAEs that do not rely on transformers and which are really expensive to train. The transformers are. And we'd also like to explore other encoding and decoding models, such as VQGANs. In acknowledgement, we'd like to thank our TA, Taresh Sethi, for his guidance. And we'd also like to thank the PyTorch Tally contributors for making the model template available. So for a baseline in our experimentation.